Good morning, dear student. In today's lecture, we are very much interested in the third chapter of our course CHG 290, that is coordination compound, the reactions and the mechanism, in which we discuss the first point, that is substitution reaction. So, before discussing the substitution reaction, one must understand the very important concept, that is the inert and labile complex. So, without discussing this point, that is, without knowing the complex, either it is labile or inert, one can does not understand the substitution reaction. So, we are very much interested in the first point, that is inert and labile complex. So, let us discuss. What is inert and what is labile complex. So the first point is that the metal complex in which the rate of ligand displacement reaction is very fast and they shows high reactivity are called labile complexes. So what is labile complex? So you all are very much familiar with this concept, that is inert and labile complex. The labile complex are the complex in which the rate of ligand displacement the rate of ligand displacement the rate of ligand displacement reaction the rate of ligand displacement reaction is very fast. The rate of ligand displacement reaction is very fast and they shows high reactivity. They shows high reactivity. They shows high reactivity. They shows high reactivity are called labile complexes. So the complex in which the rate of ligand displacement or the rate of ligand substitution is very much higher and they shows high reactivity are called labile complex. Okay, and this property it is termed as lability. On the other hand, if you consider the metal complex in which the rate of ligand displacement reaction is very slow and hence they shows less reactivity are called inert complexes. So on the other hand, what is inert complexes? The complexes in which the rate of ligand displacement the rate of ligand displacement is very slow. The rate of ligand displacement is very slow and we can say that this shows less reactivity. This shows less reactivity. This shows less reactivity are called labile complex. Are called sorry They are called as inert complex. The rate of ligand displacement is very slow and they shows less reactivity. They are called inert complex and this property is termed as the inertness. Okay, whatever the properties shown by these complexes is considered as inertness. So at least you should know what is labile and inert. The rate of ligand displacement or the rate of ligand substitution reaction is very fast. In those complex, they are considered as a labile complex, while the rate of ligand displacement is very slow and this shows less reactivity towards substitution. They are considered as a inert complex. So let us discuss some important points regarding to this inert and labile complex. The first one, that is the labile and inertness, that is lability and inertness on the basis of VBT, that is valence bond theory. So how one can predict either this complex is labile or inert? So the first important point is that the labile or the lability and inertness, labile and inertness, labile and inert on the basis of VBT, valence bond theory. So how this VBT can explain the lability and inertness? Let's discuss one by one. So we know that. So when you consider the valence bond theory, then we know that there are two types of complexes. One is outer orbital complexes and another is inner orbital complexes. So we already know that outer orbital complex having sp3d2 hybridization and inner orbital complex having d2sp3 hybridization. So let us discuss about outer orbital complexes. Outer orbital complexes. So for outer orbital complexes, the complex having sp3 d2 hybridization, the complex having sp3 d2 hybridization are generally labile. So the complex, they are considered as the outer orbital complex which having sp3d2 hybridization, and they are considered as a labile complex. They are considered as a labile complex, or they are considered as a labile in nature, uh, by they are labile in nature according to this valence bond theory. So this VBT proposed that the bonds in sp3 hybridization, sp3d2 hybridization, are generally weaker than d2 sp3 hybridization. So what is the reason why these outer orbital complexes, or the complex which shows sp3d2 hybridization, are labile complex? Because the second point is important, that is, whatever the bond, that is bonds in sp3 d2 hybridization is a weak bond, generally weak bond. Okay, so whatever the bond in sp3d2 hybridations are weak bond as compared to d2 sp3 hybridization, d2 sp3 hybridization, and therefore they shows labile character. Because the bond is very weak, so the bond can break very easily, and the substitution is occur very easily, and therefore this outer orbital complex, they shows sp3d2 hybridization, are considered as a labile complex according to this valence bond theory. Okay, for example, if you consider the example, that is octahedral complexes of Mn plus 2, Fe plus 2, and then octahedral complexes of Mn plus 2, Fe plus 2, and chromium plus 2 shows fast ligand displacement. Shows fast ligand displacement. Shows fast ligand displacement. Shows fast ligand displacement. So this is according to the valence bond theory. So according to this valence bond theory, the outer orbital complex which shows sp3d2 hybridations are labile complex, because the bonds in this sp3d2 hybridations are weak bond, and this bond can be easily break, or easily the ligands can be easily substituted by another ligand, and therefore the rate of ligand displacement, or the rate of substitution, is very much higher, and therefore they are considered as a labile complex. The example is given, that is the octahedral complexes of Mn, Fe, and chromium plus 2 complexes. Let us discuss about the outer orbital complex. So no doubt, that is inner orbital complex, because we already discussed about outer orbital complex. That is outer orbital complex, those having sp3d2 hybridization, they are considered as a labile, because whatever the bonds are very weak bonds. So let us discuss about second, that is inner orbital complex. That is second, inner orbital complex. Inner orbital complexes, or inner orbital complex. So they are having d2sp3 hybridization. So we are very much familiar with this inner and outer. So this inner orbital complex having d2sp3 hybrid orbitals are filled with 6 electron pair donated by the ligands. So if you consider this inner orbital complexes, in this inner orbital complexes the hybridization is d2sp3. Okay, and the hybrid orbitals are filled with 6 electron pair The hybrid orbital are filled hybrid orbitals are filled with six electron pair six electron pair donated by the ligands. Six electron pair donated by the ligands. The d electrons of metal will occupy. So if you consider in this d2sp3, the d electrons of metal will occupy dxy, dyz, and dzx. So this is the inner orbital consists of d2sp3 hybridization, and the hybrid orbitals are filled with 6 electron pair donated by the ligands. The d electrons of metal will occupy dxy, dyz, and dzx orbital. Okay, and this d2sp3 can form. Okay, so they occupy dxy, dyz, and dzx orbital, and this d2sp3 can form both inert or labile complexes. So we already discussed that the outer orbital complexes having sp3d2 hybridizations, they are labile in nature. But if you consider the inner orbital complex, those having d2sp3 hybridization, in which the hybrid orbitals are filled with a 6 electron pair donated by the ligands, and the d electrons of metal will occupy in T2G orbitals. The d electrons is occupied in T2G orbital, and therefore if you consider this d2sp3 hybridization or this inner orbital complex can form both inert or labile complexes. Okay, let's discuss the some important points regarding to these inner orbital complexes. That is, in order to show the lability, one orbital out of dxy, dyz, and dxz must be empty so that it can gain another electron pair and can form 7 coordinated species, which is a necessary step for associative pathway of ligand displacement. So we know that this inner orbital having d2sp3 hybridization, okay, and the electrons are donated. The 6 electron pairs are donated by the ligands, and the d electrons of metal will occupy in T2G orbit, that is dxy, dyz, and dzx, which is completely filled. So in order, so let us discuss in order. So we are considering the inner orbital complex. Okay, in order to show lability, in order to show lability, one orbital out of dxy, dyz, and dzx. So for inner orbital complex, to show lability, one orbital out of dxy, dyz, and dzx must be empty so that it can gain another electron pair and form 7 coordinated species, which is a necessary step which is a necessary steps for associative type of mechanism. Steps for associative, that is SN2, for associative uh, type of ligand displacement, associative type of ligand displacement. So in the next lecture we discuss about the different types of mechanism for substitution reaction, that is associative, dissociative and interchange. In that lecture we you are very much clear about what is associative, what is dissociative and what is interchange, but at least you should know for inner orbital complex to show lability, one orbital out of that T2G orbital, that is dxy divided dzx, must be empty so that it can gain another electron pair and form 7 coordinated species, which is necessary step for associative type of mechanism. So in associative type of mechanism, the whenever there is association, the coordination number of intermediate increase by 1 unit, and then after that there is a dissociation. So you should keep in mind, in associative the coordination number of intermediate increases, while in dissociative mechanism or dissociation type of mechanism the coordination number of intermediate decreases by 1 unit. So this is the necessary step for associative type of mechanism. Okay, so in order to show lability, one of the orbital must be empty, and therefore when the orbital is empty it can gain the electron pair from another ligands and form 7 coordinated species. Okay, and then it becomes labile. On other hand, if all this T2G orbital contain at least one electron, okay, if you consider, on other hand, if you consider the second case, that is all this orbital, that is dxy, dyz and dzx orbital contain at least one electron, it will be, then it will be it will be it will be it will not we can consider it will not be able to, it will not be able to it will not able to gain electron, it will not able to accept electron or gain electron pair from incoming ligand, from incoming ligand from incoming ligand, and hence it is expected to shows inert character, and it is expected to shows inert character, that is both this dxy, dyz and then dzx contain single electron, then it is stable and it cannot gain or accept the electron pair from the incoming ligand, and therefore in this case it is inert. For lability, we already discussed that one of the orbital, that is dxy, dyz or dzx must be empty for lability. So we can consider one of the orbital is what, empty. We can consider this as what, this is an empty orbital, so only 2 electron is there. Okay, and this orbital is empty, for lability, okay. So this is all about the lability and inertness on the basis of valence bond theory. In the next lecture we discuss about the lability and inertness on the basis of crystal field theory, and then we discuss in the next lecture, that is the different types of mechanism for substitution reaction, that is associative means SN2, dissociative means SN1, and the interchange mechanism. So, okay, thank you.